Hello and welcome to electricity lesson number 1. So this is the introductory demonstration for the class for this scheme of work on electricity, in which we're introducing students to the concept of electricity using the concept of static electricity. For this experiment we need the following apparatus. Right, for this demonstration in electricity lesson number 1 using static electricity we need the following apparatus. There are 7 different demonstrations here. So first of all we need the Vandergraff generator, then we need a discharge bulb, then we need the spinning star, then we need the horsehair tail, then we need the Faraday pails, then we need the fluorescent tube, the dancing ball container. If you've got access to a little bit of real fur, a small amount of little real fur, and some pie tins. Okay, the very start of the demonstration is to show the generation of static electricity. Now nearly every child and every person has experienced static electricity, certainly from hot days when they get out of a car and this little spark gets them as a little bit of charge discharges from them through the car into earth, which they normally accumulate as a consequence of rubbing around in the car from their clothes with the car seat. So in approaching the Vandergraff generator, it's basically composed of a belt and a dome and some wheels. The wheels are made of different materials, and essentially as you wind the Vandergraff round, the belt turns past the wheels, and through the abrasive action of friction contact with the wheels, they rub electrons off. And the electrons then jump onto what's called a comb, and then they pass up the belt and then onto the dome, past another comb inside. The electrons are negative, and the whole concept of that we're introducing in this particular lesson and this demonstration is that electricity is the flow of electrons. It's made of electrons, and in this context we can actually see some of the electrons, rather a large quantity, of when they discharge. Okay, so what we're going to do is just show that discharge using the discharge bulb. So connect up the leads to your Vandergraff, and what's actually going to happen here, as I turn the lever, electrons are going to gather on here, and when I bring the dome, the discharge bulb, to within about 4 centimeters or so, and when the voltage has built up enough, you should see a discharge from the dome to the discharge bulb. The electrons will then come down here, transfer back through the wire to the generator, and this is how you do it. So allow a bit of charge to build up first. Okay, and now on to the other 6 demonstrations. I might add just before we do that actually that the previous demonstrations and a number of these ones are actually best done with the lights subdued and quite dark, particularly the discharge dome or bulb. For the rest of them though, apart from the fluorescent lamp, these are probably best done in good strong light. Okay, in between each of the demonstrations you are going to build up a bit of charge, or quite a lot of charge, depending on the atmospheric conditions. If it's very moist, you may have to have a hairdryer to continually dry the belt in between demonstrations and the dome. But if it's a nice dry crisp day, which is exactly what you really want ideally, then you're going to build up some charge on the dome. In a very neat little way of discharging that safely rather than get a little tiny shock is to use a pair of scissors with some rubber handles. And so I'll show you this. So there's no charge on here, so it's perfectly safe. If I build up a little bit of charge, now I can see this if I just edge my arm into it, you can see a little bit of crackling as it discharges through the cloth material. But another way, simple way you should do before you go on to any of the other demonstrations is this. So build up some charge. So I know there's charge on here now. You get 2 points, and if you touch the 2 points, make sure your hands are on the rubber together like that, and just swipe away, the electrons will come through you quite safely to Earth, and it's safe. Okay, for demonstration number 2, we're going to use the spinning star. It's got a number of different names depending on where you buy the equipment from, and actually I quite like to call it the electron star. As you can see, it's a very sharp tip, and the star itself sits on that tip, so very low friction point there, and if you give it a little tiny spin you can see that it spins. or a little push rod that spins. Okay, now an interesting little bit of Newtonian mechanics here. The theory behind this is that as the electrons accumulate on the dome, as I turn the Vandergraff round, they will conduct up through the metal spike onto the metal wheel here, the star, and all the electrons, almost at an equal rate, will come to the particular point, and they'll slowly leak into the air or discharge to air. Now, if you imagine you were a little tiny electron on that point, and the analogy would be kind of similar to a diver on a springboard. As they leave the point of the star, they provide a little tiny bit of inertia here to push in that direction. That's the kind of theory. Now, if that is true, theoretically, given that there will be millions of little electrons on each one of these points as it spins round, if I were to turn the star in this direction, as I crank this round and all the electrons are leaving the point, theoretically it should slow down and reverse its direction. So let's give that a try. So place the needle firmly into the dome of the Vandergraff, then sit carefully the star or electron star onto the spike. Hopefully it's a really nice crisp day. Give the star a little push, not in the direction of the points, but in the opposite direction. So in that direction there. And then, with some reasonable force, crank the generator and see what happens. So as you can see, it's slowly starting to slow down. It's now come to a complete stop. And rather magically and wonderfully, it's now moving in the opposite direction. So all the little electrons are gathering on the top, conducting here along the point and pushing off and pushing the star in the opposite direction. And just to show you the discharge tip from last time, there will still be charge on here. You see it slowing down. There's the amount of electrons pushing off here is different. So take your scissors and discharge it slowly like so. No discharge. Demonstration number 2 is the horsetail apparatus. So this is composed of a little pin again which goes into the top of the Vandergraff, and a whole series of very fine filaments that kind of represents a small horsetail, a very neatly trimmed horsetail at that. And the theory here is that as the electrons move up each one of the little tiny filaments, each one of the filaments will become negatively charged, and as such they will then repel each of the other little tiny filaments, and so it should bushel out a little bit. I'm not entirely sure that bushel's the appropriate term, but let's just see if that then works. Again, it's a good idea before you do this to make sure it's nice and crisp and dry and it's not moist. It hasn't been sat in a kind of moist, damp box for the last couple of months or something of that nature. Okay. There we go, very sweet. This is a very similar one to where, for example, if I got, at the end of the year, a lot of that Christmas tinsel and stuck little bits to my hair and I held them at the Vandergraff, I could actually make the tinsel separate on my head. In this demonstration, we're going to use the so-called Michael Faraday, or the Faraday pail apparatus, named after Sir Michael Faraday, who was one of the most significant contributors to the world of physics of all time. Absolutely amazing scientist, and we're going to come across him several more times during the course of this particular unit. Okay, effectively the apparatus consists of an aluminium pail connected to a pin with a small piece of conducting foam. And the theory here, very simply, is as I wind this round, again, the whole pail will become electrostatically charged, and initially the small particle on the edge will attract a number of electrons. They will stick to it and force itself apart from the pail, which has a field, an electrostatic field apart from it. So we'll try that. Now, wonderfully, the field of the electrons are slowly leaking back into the atmosphere and way back down the dome as well. And as they do so, you can see the little tiny suspended element slowly creeping right back towards the edge of the pail as the strength of the field decreases as a consequence of the electrons leaking away to the atmosphere. And we'll discharge that and you can see it rush back through. Okay, and for demonstration number 4, what we've got here is the dancing balls apparatus. So we have a plastic tube with a metal top and a metal base connected obviously to the metal pin, and inside we have 4 aluminium coated polystyrene balls. So they're very light. So again, the theory is we've got a whole pile of negative electrons accumulating on the dome as I wind the Vandergraff up, and as they conduct up through the pin onto the plate, each one of the little metallized balls in contact with the plate will become very negatively charged, and their negative charge will act to repel each other. And because they're quite light, and the force of the charge that's available, the force generated by the charge, is sufficient to cause them to bounce about. Now, very interestingly, what is actually happening here is that the balls, a bit like the balloon when you hit the party balloon, which we'll do a demonstrate in a separate demonstration. When the ball surface is very, very negative, as it touches the wall, it forces the electrons, some of the electrons, away from the plastic, leaving a positive side, and that forms a point of attraction. And if we discharge the whole apparatus, then all the electrons are gone and therefore the charge is in balance again. Okay, in this demonstration, we're going to do something really unusual. These are flying pie tins. And a little tip, so you need a whole pile of little tiny Mr. Kipling's pie tins. But a nice little tip is to get the basal tin with a little bit of sellotape onto it and fix that onto the top of the Vandergraff, just lightly. And of course there's going to be a little bit of stickiness left over from the sellotape at the end of this demonstration, in which case you just need to give the dome another clean and polish and get rid of that residual stickiness. So then you put the pie tins on like that. And so the theory here is that these pie tins, the individual aluminium pie tins, are very light. So as I generate charge onto the dome, the pie tin itself, who's on contact with the dome to start with, will conduct all the electrons, all the charge will pass up to the top of the pie tin, which will become negative. They all become negative, but this particular one will become negative, but there's nothing preventing it from rising, whereas the dome, the pie tins beneath them have got pie tins on top of them. So when the electron and the charge accumulates on the top of this one, the base is obviously negative because it's got a lot of electrons on it. This one's negative, so the charge collectively here creates a field which will force, hopefully, the pie tins off in sequence. So let's see how that works. It's quite a good idea to generate quite a bit of charge, so hold the thing firmly and do it quite quickly to start with, and let's just see that work. car pickup but with turns. Okay, this is an unusual kind of extension demonstration for the Vandergraff. And it's one of the really nice ways of actually demonstrating the field, the sort of electromagnetic field that is generated on the Vandergraff. However, there is a small catch. You will need a small pet, a cat ideally, that doesn't mind donating a little bit of fur through a quick shave. But if you don't mind that, and it's perfectly harmless for a cat of course, if you could give a little tiny bit of fur, and here's a little bit of fur that our cat has donated, and you put the fur into the little aluminium pie tin. I have another little pie tin onto the dome itself, and sellotape this one to the base of it to the top of the other pie tin. I'll stick another bit of tape onto the other side to secure it. So a little word of warning, it's a good idea to have some safety specs here, and also to have a small hoover on hand, because this stuff goes everywhere, but it's really rather wonderful when it takes off. So what we're going to do here is, again, accumulate a whole load of charge onto the top of the dome, which will then be conducted through the aluminium pie tins and into the fur in the pie tin. Now each tiny little strand of fur will become electrically charged, and they will repel each other in a sort of a frenzy of leaping bits of fur, I hope, and we should see. Okay, let's see how this works. So suddenly the rest of it, sometimes it resolutely stays stuck in the bottom, but as you can see, on really good days, if you get the really fine separated fur, it'll shoot out into nice little obviously circular pattern around and describing the field of the dome. And these little pieces here you can see suspended neatly following the trajectory of the field here. If I bring my scissors and discharge the dome, you can see it should collapse back. Should do. And actually, once you've discharged it, if you give it another little go and spruce it up a little bit and free up some of the fur a little bit, we should have another little go. Why not? So free it up a little tiny bit. Oops. One last little go. Okay, in this demonstration we're going to use a really interesting little bit of apparatus, the fluorescent tube, to explore further the effect of the field created by the accumulation of electrons on the dome. This is really interesting because it also links within the Sullivan Science scheme of work to the light scheme, where the students use a plasma ball, and that similarly generates a field which can excite other reactions. So here, unfortunately, because of the fairly weak impact, but it is a noticeable impact, we're going to have to go dark in a second. But what I'm going to do is I'm going to generate a large accumulation of charge on the dome, which will create a field, and we're going to explore that concept of field in one of the first experiments in this lesson. And using the field generated here effectively does the same thing as when one of these fluorescent tubes is placed in a circuit in the house. Okay, so without much further ado, I'm going to accumulate a bit of charge and watch what happens to the tube. And that, ladies and gentlemen, nicely brings us to the end of the electrostatics demonstration. I'm absolutely certain your children and you are going to have an absolute ball when you're doing these demonstrations. And don't forget to discharge every time, treat the equipment with care, and I hope that certainly have enthused your children with the joys of electrostatics. Thank you.